Welcome to qnawire.
This is problem number 28 of chapter 23. In problem 26, we saw that the equation for the first order angular deflection for the diffraction minimum was given by W sine of theta 1 is equal to lambda. In this problem, we're given three different widths for single slit diffraction, and we're asked to find this first order angular deflection angle for the diffraction minimum. So we solve this equation here for theta 1. So sine of theta 1 is equal to lambda over W, and then we take inverse sine on both sides. So this is the expression that we're going to use. The light shined onto the slits is lambda equal to 630 nanometers. Now, if the widths are given in nanometers, we don't need to make any conversions. However, the widths are given in millimeters, so let's go ahead and convert everything to meters. That's the wavelength being shined on the slits, and then we have three of them. So let's do the first one. For the first single slit, we have a width of 0.020 millimeters, which is equal to 0.020 times 10 to the negative 3 meters. To find the first order diffraction minimum, we just apply this equation and substitute the values. So for lambda, we go ahead and grab the wavelength. And for the width, we grab it here. Okay, so in degree mode, this comes out to approximately 1.8 degrees. So this is for the first single slit. Let's go ahead and copy this. The only thing that changes for the other two is the width. So this is going to be the second one. All we have to do is change the value for the width. The width of the second one is 0.20. So all I have to do is delete that 0 here. And then when we plug this into the calculator, you get 0.180. Now, why is this the case? Well, notice that all we're doing is we're shifting the decimal place to the right one here. So if we're shifting it to the right for the width, if we're shifting it to the right one, overall what that's going to do is shift it to the left of this whole term. And since we are dealing with small angles, sine of theta is approximately equal to theta. So whatever value we get here, if all we're doing is shifting this decimal place to the right in the denominator, that shifts it to the right here overall in the overall term. So that's what's going on here. Because of small angle approximations, you can see that even though we're doing multiplication by 10 here and we're doing an inverse sine, the result is a multiplication by 10. That's only possible if we're dealing with this small angle stuff. Okay, so this is the second slit. Let's go ahead and copy this and work on the third one. So for the third one, we have a slit width of 2.0. So again, what did we do? We divided by 10. We divided by 10 here. We multiplied by 10 here in the denominator, so that's a division overall by 10 of this term, of this argument. So let's go ahead and just plug it in. It's going to be 2.0. If you go ahead and calculate this, this comes out as you would expect, 0.018. So since we multiplied by 10 in the denominator, that's like dividing the whole term by 10. And if you divide the whole term by 10, that's what happens here for small and L approximations, because sine of theta is equal to theta here. So here we're applying this equation for the first order diffraction minimum of single slit interference.